And we're back. Welcome back from the weekend and happy Tuesday. Today we're going to continue on with our discussion about events, and we will look at set notation and set operations and how we use them to construct events and get into the formal definition of probability. This when can I see you again? So before we do so, we'll go over some administrative bits. At Barron Chapter 1, pages 1 through 4, Barron Chapter 2, pages 9 through 14. Again, also, Homework 1 is due out this evening, September 1st, at 1 second before midnight, at 11:59 and 59 seconds p.m. Please make sure you are doing work every single day. If you do so, you will find you will be ready and carefree. Otherwise, you can expect to anticipate impending doom. Please make sure you're doing work every single day, follow the instructions for the homework, and do not wait until the last minute to submit it. Give yourself ample time. So before, when we left off, we talked about more complex events, and we discussed first the building block using simple event, which was the roll of a single die. Roll of a single die, all the possible outcomes, we called sample space omega die, the cardinality of which n equals 6. We extended that to looking at or thinking about the number of events of a more complex type of event, namely the set of events corresponding to an experiment for n rolls of a single die. And the question we asked, what were your observations? So we had spaces for each of those big N many rolls, and we identified the outcome for each roll, and we said that the number of choices multiplies over all of the big N many rolls for a total of 6 to the big N power as the number of different choices, and therefore the number of different events. We said the probability of a particular outcome, that is a string of roll outcomes, big N long, the probability of a single instance of an N many, big N many rolls of a die, because each die roll outcome is equally likely, it's random, we express that probability, that when can I see you again, as 1 over the cardinality of that sample space. So our sample space has 6 to the big N many different outcomes we can observe. We take the cardinality of omega n rolls of the die. We say 1 over that cardinality, which is 1 over 6 to the big N. Okay, so let's continue on with our conversation and look at set operations. So let's define two sets, A and B, and an event is in a set, and our event, which we'll generically call E, we could say for the roll of a die that E is equal to this statement, not odd. Well, let's consider that. I'll set my pen. I think I'm going to use blue today. So we know that omega die, single roll of the die, is the set of all of the observable outcomes 1, 2, 3, 4, 5, and 6. So if we said our event E is equal to the set corresponding to not odd, well, what does it mean to be not odd? What does that mean? Well, let's think about this. If you're not odd, that means that you must be even. So this event E, not odd, must correspond to those outcomes of the die roll that are even. So that would be 2, 4, 6. There's our event called not odd. Well, what about this other event greater than 2? Let's think about that and have that as an exercise. Well, if our event E is equal to greater than 2, okay, if our sample space omega greater than 2, well, is 1 greater than 2? No. Is 2 greater than 2? No. 3 greater than 2? Yes. How about 4? Yes. How about 5? Yes. How about 6? So E greater than 2 is the event E for the die roll corresponding to 3, 4, 5, and 6. So if we want to construct arbitrary events, we must be able to take simple events like the 1, the 2, the 3, and combine them to make complex events. So in constructing our complex events, we're going to need the machinery of set operations. Okay, so let's take a look generally at set operations. If we have some set A, and let's say A is equal to the event 2 and 4, and let's say B is equal to the event 6, if we wanted to construct the event called not odd out of A and B, we would combine the two through the union set operator. So this is what union looks like. We take all the elements of A, and each point here is an element of A. Here's my set A. And we take all the elements of B, we combine them, and as a set, it means that they do not have duplicates. Likewise, this is set intersection, and we have an assignment where you implement set intersection using cell arrays in MATLAB. Set intersection are all of those elements that are common to A and B. Single copy because it is a set. So if we write A, B here, you'll notice this shaded region are those elements that are common to A and B, and of course using Venn diagrams from discrete math, which is a prerequisite of this course. Likewise, set operation not A, well, here we said not odd. So if we have the full sample space omega, which is 1, 2, 3, 4, 5, 6, all of our possible outcomes, if we said not odd, okay, what is odd? Odd are all of the events 1, 3, and 5. Now, if we said not odd, well, we mean everything that is not, or the complement of everything that's an odd. Well, we know from this, if we said A is the total set, right? And not odd is everything outside of A. So if odd is 1, 3, and 5, well, everything else that completes the entire set of possibilities, not odd, would be 2, 4, and 6. And so the complement is calculated by taking everything that's possible and removing from it those things that are odd in this particular case. Now, we also have set difference. Set difference, A, difference B, is equal to everything in A that is not in B. So here we have set A, here we have set B, and you notice the section that intersects with B, that's empty, and we have the shaded region, which are all those things in A that we cannot find in B. Okay, so if we said B is everything that's greater than 2, well, that would mean B for the die roll is 3, 4, 5, 6. So if B were 3, 4, 5, and 6, for example, well, everything that's in A but not in B, well, that would be 1 and 2. Okay. So this set difference is everything that's in A is not in B. So you're going to take the things in B, not in A, that's here, and you're going to also remove those things that are common to A and B, which consequently this region is A intersect B. Okay. So we use the machinery of set operations from discrete math to construct complex events out of what we're going to call a simple or a singleton event. So a simple or singleton event, E, might be the one outcome from a single die roll. Okay, so we need set operations in order to implement the machinery that we'll use to construct complex events. So let's consider events in general. If we have two events, A and B, they are considered or called disjoint if the intersection is empty. So what does that mean? It means A and B do not share any elements. So let's say A is equal to the set of evens from the die roll. That would be 2, 4, and 6. And let's say B were the set of odd outcomes from a die roll. That would be 1, 3, and 5. If we were to look at what's common between A and B, the intersection, they share nothing in common. Therefore, they are disjoint because A intersection B would be equal to the set 2, 4, 6 intersect with the set 1, 3, 5. They do not share anything in common, so that result is the empty set. Therefore, evens and odds, those two sets from the die roll, from omega die, are called disjoint. Okay, so suppose you have a set of events. It doesn't matter what they are, but we note the first event A, the second one A2, A3, A4, so every 1, 2, 3, 4, etc. If they are mutually exclusive, also synonym for that, pairwise disjoint, that means that for any two events from this set, A1, A2, A3, and so forth, they're pairwise disjoint, meaning their intersection is 0. So let's consider all of the singleton events from the die roll. So we have, let's say A1 is equal to the 1 outcome, A2, if that were equal to the 2 outcome from omega die, A3, if that were the 3 outcome, and let's say A4 is the 4 outcome. Likewise, A5 is the 5 outcome from the roll of the die, and A6, lastly, is the 6 outcome. Now, for all of these events, A1, A2, A3, A4, A5, A6, if we take the intersection between any two, that's empty set. So 1 intersect with 4, that's empty. 1 intersect with 6, empty. 3 intersect with 5, empty. So for any two pairs of events, if they are mutually exclusive, that means that any two pairs intersect with one another to give you the empty set. Okay. Likewise, given a set of events are called exhaustive if their union is the entire sample space omega. So how would we make the sample space omega from each one of these singleton events, A1, A2, A3, A4, A5, A6? Well, remember, omega die is equal to 1, 2, 3, 4, 5, 6, which is the same as the union between the singleton events for 1, 2, 3, 4, 5, and 6. So therefore, omega die is the set that we get representing all possible outcomes if we take the union of the 1 outcome with the 2 outcome, with the 3 outcome, with the 4 outcome, with the 5 outcome, and with the 6th outcome. Now, substituting for what our singleton events are, that would be omega die is equal to A1, first event, union A2, union A3, union A4, union A5, union with A6. So if we take the union of all of these 6 different singleton events, A1 through A6, we get the complete sample space omega die. Now that's called exhaustive. A set of events is exhaustive if the union of each of them is equal to the entire sample space, the whole sample space, in this case, omega die. So there's an important property when we talk about events that we can use to construct all possible events that we can describe from a sample space omega, this idea of mutually exclusive, i.e. pairwise disjoint, and exhaustive. Another way of saying this is mutually exclusive and collectively exhaustive. This is going to be a tool that we're going to use to be able to describe things like evens or odds from all of the singleton events. And we'll use this machinery in our description of probabilities. Okay, so let's take a look at the rules of probabilities, and this definition, 2.9, is from the book. So first, we choose something called a sigma-algebra. A sigma-algebra, and there's the symbol we're going to use for this sigma-algebra, and it's a sigma-algebra of the events on our so-called sample space. So the sigma-algebra, M, is going to do something on all of the possible events from our sample space. For example, sample space omega die, which represents all the possible outcomes of our die roll, which is 1, 2, 3, 4, 5, and 6. Now, we just had an example on the previous page where we talked about evens. And we said the evens are equal to those outcomes that are not odd or the same as 2, 4, 6. And this 2, 4, 6, we can build it up as being the union of that event corresponding to the 2 outcome with the event outcome for the 4 with the event outcome for the 6. So if we're going to arbitrarily talk about every possible thing we can observe for a die, we need to be able to describe this when can I see you again on all possible combinations from the sample space omega. We use set operations to construct them, but we need machinery that'll give us this notion of possible combinations. And this operator or function that gives you possible combinations is called a sigma-algebra. The sigma-algebra operates on this sample space omega, and sometimes in the literature you'll see sigma written as lowercase sigma, Greek letter sigma, and you'll see it written as a function operating on the sample space. And so what this operator sigma does, or sometimes you'll see script m operating on the sample space omega die, it'll be the function, the sigma-algebra, that returns to you combinations of the singleton events constructed by set operations. Okay, so let's look at this sigma-algebra. You choose a sigma-algebra, a set of possible combinations on sample space omega, and it's a collection of events, and these events are going to be associated with this thing we'll call a probability. We'll get to what that means later. And you consider this in your problem. So a sigma-algebra will select some set of combinations of your sample space omega events, some combination of singletons that are the only combinations that you consider when you talk about this when can I see you again, your probabilities. Okay, so you have a collection of events, or sigma-algebra, on a sample space, and you consider it as a valid set of combinations if the following things are true. And this talks about how you construct the combinations. What has to happen? It includes a sample space. What does it mean to say omega? Well, it says I roll my die. Here's my die. And I have the event corresponding to everything that's possible. Sample space is one of the combinations. That means I roll the die, and something's going to happen. I get a 1 or 2 or 3 or 4 or 5 or 6. So the anything event is one of the combinations in my sigma-algebra. Okay? So my sigma-algebra, script M, is going to include, it is a set, all the combinations of events that I can construct. One of them is going to be omega die. in the case of the die roll. Okay, so what else is in my sigma algebra? Sigma algebra. Okay, so we have the anything event, some side of the die is going to happen. Okay. We also have, for every event that's in your sigma algebra, not only is that event contained, but its complement is contained. And you'll notice here, for E, they made no distinction. So for every event that's in there, you have its complement. So, okay, let's think about these events. You could have the event consisting of the one outcome. So we didn't make any distinction about what that event is. So for every event you can think of, its complement is also there. So if we have the event E, I'll write it in this column, and we have the complement not E, our set operation, not E, given event 1 outcome being in the sigma algebra, one of our combinations, that means everything that's not 1, which is 2, 3, 4, 5, and 6, will also be in your sigma algebra M. So in the sigma algebra M, I'm going to have 1 as well as not 1, 2, 3, 4, 5, and 6. Likewise, I'm going to have 2. That's another event I can think of, in addition to not 2, which is 1, 3, 4, 5, and 6, etc., up to and including 6, which is another event I can think of, and not 6, which is 1, 2, 3, 4, and 5. Okay, so we know so far the combinations of events for the die roll, the sigma algebra for the die roll, includes the anything event, and it includes the 1, not 1, 2, not 2, 6, up to and including 6 and not 6. Now, if we include the anything event, what is the complement of omega die? Well, that is our empty set. Okay, so we have the anything event, and then we have all events we can think of because we set no restriction on E. And if you have E, it means you also have not E. Okay, so now that we have our basic elements and the complements, we also have this last point. Every finite or countable, finite means it ends, countable means we can draw one-to-one correspondence with the naturals. So for every finite or countable collection of events in M, it's contained along with its union. Okay, so what is a countable collection? So a collection is the one event. We can have the one event and the 2 event. We can have the 1 event with the 2 event and the 3 event. So for every collection of events that you can form, you also have the union of them. So the 1 event union, okay, that's just the 1 event. 1 and the 2, the union of those is equal to the event 1, 2. The union of 1, 2, and 3, that should be a 3, is the event 1, 2, and 3. So what does that mean? We can have the singleton events. We can have the events that represent every 2 events from omega die, every 3 events, every 4 events, and so forth. So that means we have event 1, 2, event 1, 3, event 1, 4, etc. All the 2-way events. We have the 3-way events, 1, 2, 3, 1, 2, 4, 1, 2, 5, etc. We have all of the 4-way events, 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 3, 6. We have all the 5-way events. We only have 2 of them, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 6, etc. And all possible combinations of doing one-way, two-way, three-way, four-way, five-way. And of course, omega die is all 6. You only have one of those. And so not only do we include the one-way, two-way, three-way, four-way, five-way, etc. events, we also have the complement because we still have to satisfy B. So if we do this, this gives us all of the possible ways we can have combinations of events from our sample space. And one of these combinations, be they singletons, simple ones like 1, or two-way, or three-way, or four-way, or the complement, now we have a way of describing all of the possibilities that we can use to describe outcomes of a single roll of the die. So when we say the evens is one of the combinations consisting of the 2, the 4, and the 6. When we say not even or odd, that's equal to 1, 3, and 5. That's nothing more than one of the three-way events. The evens is nothing more than one of the three-way events. And so this machinery in definition 2.9, and it's in the book, it gives us all of the properties we need in order to construct all of the possibilities we can have for any type of observation related to the roll of a die. Okay. So let's take a look at the degenerate cases, the simple cases, on through the most complex case. And so every sigma algebra, based on the conditions that we defined about the everything event, here's my everything, and its complement, well, that means the sigma algebra, the simplest it can be, the degenerate case, is saying if I roll a die, any outcome of the die can occur, or no outcome of the die can occur. That's the simplest, or the degenerate sigma algebra, degenerate. Likewise, the most rich sigma algebra that we can have, it has every possibility imaginable. And this every possibility imaginable that we describe as being this every possibility imaginable we describe as satisfying these three properties, A, B, and C, in definition 2.9 in the book, well, that's nothing more than the power set. And this is the richest description you can have because it's all possible combinations of elements from sample space omega. So it's the collection of all possible events, our power set, which you covered in discrete math. And so if we have this most descriptive, richest sample space, richest sigma algebra script M over our sample space omega, it has a total of 2 to the n events. And those 2 to the n events would be the count if we were to enumerate all possibilities. Okay. Now, it's easy to talk about the power set about omega coin flip because we have a heads and a tails. Well, let's draw that out. The sigma algebra, the dense sigma algebra for omega coin, right? It has a cardinality of 2, so that's 2 to the 2, that's 4. Well, let's see. It has the anything event, heads, tails. It has the nothing event, empty set. It has the one way. It has, let's see, it has heads. And it has the complement of that one way, which is tails. And we've now exhausted everything. So all possible outcomes you can have for a single coin flip, here's our coin, is you can have either a heads or tails. You can have nothing happen. You can have a heads. You can have a tails. And that's the richest form of our sigma algebra, most descriptive. So where are we going with this? Let's take a look at the when can I see you again. So what is actually a probability? We said a probability talks about what we call the when can I see you again. We said when we have a stochastic system, the outcomes can be many. You have a coin flip, but we don't know. It's non-determinate. It can be a heads, it can be a tails, but it's not always the same every single time. And so if you're going to describe the behavior, you have the experiment, you flip the coin, you have the observation, what you see, and you have the when can I see you again. When can I see you again? Wixia. All right, so you're going to pronounce that. So we have when can I see you again. With this when can I see you again, we said it describes the proportion per centum, or the percent, corresponding to the proportion of times that we're going to see a particular outcome, in this case the heads or the tails. So a probability is defined, this is definition 2.10 in the book, more formally as we have a sample space, omega, the observations that are possible to see. We enumerate out our observations. This is our omega sample space. And we have a sigma algebra of the events on it. So we have the observations, and we have all possible combinations of those observations, omega, as a sigma algebra. The probability then is a function that inputs the combination of events, and it outputs a number between 0 and 1 on the real number line. Now, the square brackets represent closed interval. So we have 0 here on the real number line. We have 1 on the real number line, and we include the endpoints along with every number in between. Well, guess what? This is a percentage per centum. So if we said 0.1, right, that's 10%. If we said 0.9, that's 90%. That's 10%. That's 90%. So what is the probability actually doing? A probability says I list out the elements in my sigma algebra. So if I say my sigma algebra associated with, let's say, omega coin flip, and let's assume that omega coin flip only had the combination consisting of heads and tails. That's one type of combination. I'm not doing the full power set. Now, what we're going to do, we're going to input the sigma algebra, right? And it says, okay, well, my sigma algebra, M, in this case, over my omega coin, it's going to have a heads element, it's going to have a tails element, and I'm going to associate it with interval from 0 to 1 on the real number line. And it just happens that I'm going to associate heads with the number 0.5, and I'm going to associate tails with the number 0.5. And so the probability is really just a function that assigns proportions per centum to each one of those combinations in the sigma algebra over our observations omega, our sample space omega. So it's a function of events. The domain of this function is the set of possible combinations, our sigma algebra, under consideration. And the range is a closed interval in the real number line between 0 and 1. So more formally, you'd write 0, 1, including endpoints, elements of the set of real numbers. Okay. Now, the following properties of this function P, or probability, has to satisfy the following properties, right? In order to be a probability, yes, you assign proportions per centum to the possible combinations from your sigma algebra, but you also have to satisfy the following properties. it has what's called the unit probability. It says that whenever you have among your possibilities the anything event, so if your sigma algebra includes, for the coin flip, the event heads, tails, the anything event, this function always pairs it with the 1 number, the real number 1. So what does that mean? It's called unit probability. It says the probability of anything that can happen is always 100%. Okay. Also, it has what's this property, second property, called sigma-additivity. For any finite or countable collection of not any event, but mutually exclusive events, pairwise. So they're mutually exclusive, meaning that pairwise, the intersection between them is empty set. So what's mutually exclusive? 1 is mutually exclusive with 2. 1 is also mutually exclusive with 3. The evens are mutually exclusive with the odds. So what does this say? It says if you want probability of the complex event achieved by the union between disjoint or mutually exclusive simpler events, that's equal to the sum of the individual events. That's interesting. So that means if I have event 1 is 2, event 2 is the outcome 4, and event 3 is outcome of 6, if I want the probability of the evens, well, what's the probability of evens? That's the union of 2 with event 4 with event 6, right? That union is the same as saying the probability of the event 2, 4, 6, which is how I construct the evens. If I want that probability, how do I do it? I take the probability of the 2 events, I add that to the probability of the 4 events, and I add that to the probability of the 6 events. So this gives us a scheme for how we calculate the probability of a complex event by decomposing it into a set operation, the union, based on the simpler events. So this is just 1/6 plus 1/6 plus 1/6. That's equal to 3/6, which is 1/2 or 0.5 probability. So if we said, what's the probability for a single die roll of rolling an even? Well, that's equal to 0.5 or 50%. And we get that 50% by deconstructing the complex event even into disjoint events, or mutually exclusive, through union, and using this property to combine the individual probabilities. Okay, so let's look at these extreme cases. If we have sample space omega, that's all possible outcomes or events. If we have the empty set, that's no events. And so the probability of the anything event is 1. That's part of the definition of what it means to be a probability. The probability of the anything event union with the null event, well, what's that? By our definition, they're mutually exclusive because omega intersection empty is empty set, right? So we have the probability of 1 of omega, which is 1, plus the probability of empty, which is 0. They are mutually exclusive. This expansion is the definition of that other property that we discussed for events of the probability of the union of mutually exclusive events. The probability of empty set is 0. Why is it 0? Okay, well, we know that this probability is equal to 1, and this probability of that is equal to 0. That's 0. Okay, and so if we know 1 plus 0, right, the probability of the sum of these is equal to 1. And so if we were to subtract this from both sides, we get 0, and we know that that's the probability of this quantity. So the probability of the empty set is 0, right? Because empty set is the same as the union of these two. We add the two together. If we know the probability of this plus this is 0, right? If we know the probability, rather, of omega, the anything event, plus the probability of empty set, if that's equal to 1, and we know the probability of this is 1, we subtract 1 from both sides, and that leaves us the probability of the empty set is equal to 0, right? Okay, so we know probability of omega is 1, of the anything event. The probability of empty, of nothing happening, is 0% per centum. All right, so we can combine events through the union operator, and let's consider an event consisting of some finite countable set of mutually exclusive outcomes or events. So each one of these events, omega, is such that omega I intersect omega j is equal to empty set. So any pair, W1 with W2, W1 with W3, W3 with W5, and so forth. Therefore, by that definition, the probability of this event consisting of a finite countable collection, if we take the union of them, that event is the same as saying the first event, union with the second event, union, ... right? That's the same as being the sum of each one of the individual probabilities of these events, right? So that's probability of the first event plus the probability of the second event, and so forth. That's the same. We can rewrite this sum in sigma notation. It's the sum of all the probabilities, all the events from that complex event. We add the individual probabilities. And so the key here is mutually exclusive and so-called sigma additivity. The fact that we can take these mutually exclusive events and we can add their individual probabilities, it gives us the probability of the complex event. And that's specifically if each one of these simpler events, omega 1, omega 2, omega 3, is mutually exclusive from one another. That allows us to take advantage of so-called sigma additivity and calculate the probability of this complex event, E, big E, on this particular slide. Okay, so let's think about events that are not independent from one another, that are not mutually exclusive. So here we have a two-way union of events. Here's A, here's B, and we're taking the union. Here we have a three-way union of events. Let's examine both of these cases. So what's the probability of A union B when it's such that A intersect B is not equal to empty set? And what does that mean? Well, in the Venn diagram, if A intersect B, if they're mutually exclusive, is not equal to empty set, that means we have A here, we have B here, and they do not overlap. That's why we can add. But here, in this particular example, they do overlap. So what is this? Is it equal to the probability of A plus the probability of B? No, it is not. The reason for that is as follows. If we look at A and look at B, we pay attention to that overlap region. This overlap region is A intersect B. Now, if we add the probabilities of these two, we end up double counting this overlap region. One copy is from A, and the other copy is from B. So if we add probability of A plus probability of B, we're double counting this overlap region that we identify as A intersect B. Uh-oh. So how can we fix this? We end up with A, B, and we count these twice when we should only count it once. Well, how do we fix it? We just subtract out one of those copies. So if we have A and B overlapping, then the probability of their union, the complex events formed by the union, is equal to the probability of A plus the probability of B minus the probability of A intersect B. Now, it just so happens this works if A does not overlap with B. Because if A does not overlap with B, well, what is the probability of A? Well, it's just, probability of A, whatever's assigned. What is the probability of B? Okay. What is the probability of A intersect B? Well, in this case, A intersect B is equal to empty set. So if we have A intersect B is equal to empty set, that's the same as saying the probability of empty set. What is the probability of empty set? It is 0. And we get probability A plus B in the case where A and B are disjoint. But if A and B are not disjoint, that intersect region is going to be some value that's non-zero, right? It's not going to be 0. It's going to be greater than 0. So if you can't assume that A and B are non-overlapping, you assume they're overlapping, and you subtract out the second copy of the intersect region. Okay, so what happens if we have a three-way union between sets A, B, and C? Let's say these are events. Well, what do? Well, you could just take the naive approach and you add A, B, and C together, and you would be wrong. Why? Well, let's take a look at this. Well, if you add A, B, and C together, let's take a look at what happens. So with A, you have A overlapping with C. That's this region. You have A overlapping with B. That's that region. And then you also have B overlapping with C. So when you add A, B, and C together, their probabilities, you end up counting these two-way overlap regions more than once. So how do you fix that up? You fix that up, like we said before, by subtracting them out. So you take these probabilities, you subtract out the overlap between A and B, you subtract out the overlap between A and C, you subtract out the overlap between B and C. Okay, so now we subtract that out, but there's a problem. When we subtract that out, let's take a look at this central region here. This is the three-way intersection between A, intersect B, intersect C. When we subtracted that out, something bad happened. Well, this three-way intersect region between A, B, and C, when we subtracted out this two-way, we also subtracted out that three-way, because the three-way intersection exists within the two-way for each of these two-way intersections, right? So when we subtract this out, we removed one copy. When we subtract this out, you remove the second copy. When we subtract out B intersect C, we remove the third copy. So we ended up removing all of these three-way intersections contributed by A, B, and C. So to fix that up, what do? We add back in. So we add in one copy of this intersect region A, intersect B, intersect C. So we take this A, we add that, and we take the B, we add that probability, take the C, add that probability, and then for the A, we subtract out A's intersect region with B, so we subtract that out, and then we take, this is A, this is B, this is C, then we take the intercept region that A has with C, we subtract that out, right? And then we take the intersect region that B has with C, we subtract that part out. And then we add back in another copy of that three-way intercept region. And I wish I had a piece of paper to demonstrate this. We end up with A union B union C, which is just all of this counted only one time for each one of these intersect regions. Okay. And that is our correct approach. So we sum their probabilities for the three-way. We fix the doubly counted pairwise overlaps, and we add back in what was completely removed, this three-way overlap region. And that's what we do for the three-way. So let's look at the complement. If we have set A in the Venn diagram, our sample space omega is the universe of consideration, all possibilities. We have some set A, which is some number of events, could be a complex event, and A bar is everything that's outside of A. So we could also compute A bar by taking our universe of consideration, all possibilities, and subtracting out that A region. And so we know that the probability of our sample space omega is equal to 1, right? And we know that A and A bar are mutually exclusive, right? A intersect A bar is equal to the empty set, okay? They're also collectively exhaustive. If we take the union of A and A bar, that gives you your universe of consideration, our sample space omega. So that means if they're collectively exhaustive, we know the probability of the union of these is the same as the probability of our sample space omega. So we take A union A bar, that's the same as our sample space omega, probability of the anything event, defined by what a probability 1 is equal to 1. So yes, they are collectively exhaustive. Likewise, they're mutually exclusive. They intersect is empty intersection. So if that's the case, if we take the union of them, the probability of their union is equal to the probability of A and the probability of A bar. Well, we know from that exhaustive property that's equal to 1, because that's the same as saying the probability A union A bar is a probability of sample space omega, right? Okay, so if we take this quantity, probability of A plus the probability of A bar equals 1. Now if we take that expression, probability of A plus the probability of A bar is equal to 1. And if we subtract from both sides of equality probability of A, that's minus probability of A here. We have minus probability of A on the right-hand side of equality. What ends up happening, this goes to 0. And we're left with probability of A bar is equal to 1 minus the probability of A. Okay. So if we have A bar, if we have probability of A and we want to know what A bar is, that's just 1, the probability of the universe, minus the probability of A. Okay? So if we said, what is the probability of the evens, that's nothing more than 1 minus the probability of the odds. So if we said, what is the probability of not 1 for the roll of a die, that's equal to 1 minus the probability of 1, right? The probability of 1, that's equal to 1 minus 1/6, which is equal to 5/6. So the probability of not rolling a 1 is 5/6, whatever percentage that is. That would be 5 times 0.1667, whatever that is, as a percentage. Okay. So these are some properties that the complement affords us, and it's based on both these basic facts, these axioms of probability, as well as our set operations and this sigma additivity and this mutually exclusive, collectively exhaustive idea. All right, so when we have events that do not overlap, if we want to compute the probability of their intersection, this is purely for independent events, events that do not overlap, their intersection pairwise is empty set. In this case, in the Venn diagram, we have them non-overlapping. There, in this case, the probability of the intersection between these events, and this is a basic property that I want you to remember, is equal to the product of the individual probabilities. Now that works for independent events, non-overlapping. It does not work if they have overlapping regions. Okay, so we're going to end there, and that's all I had for today. Please make sure you keep up with the reading. You might think you're working like a dog, but you are running the marathon and not a sprint. So please make sure for everything you're starting right away and you're doing a little bit every day. And these dog days of the semester will certainly be over in another 14 weeks, well before you know it. With that, we'll end there. I will see you all on Thursday, and as usual, stay healthy and stay safe.